In this part of the lesson, we're going to talk about first partial derivatives, but first we're going to start with first partial derivatives at a point. Let's review this in R2. So taking functions where we map from one-dimensional space into one-dimensional space. For example, y equals f of x. We input x and we output y. Here we say that dy dx at a point, so at x equals a. If you remember, the limit as h approaches 0 of f of a plus h minus f of a all over h. And then for some other notation, we say f prime of a, Lagrange notation. Here h is representing change in x. Now, if we talk about being in R3, three-dimensional space, where we map from R2 into R1, for example, we could have z is a function of x and y. We input xy and we output z. Now, since the function depends on both x and y, we're going to use some different notation here. Here, I'm going to say the partial derivative of z. I'll use the term par, which is short for partial derivative. So par z, par x. Now, we use this notation because the function does not depend only on x. And we're going to calculate the partial derivative at the point AB. See, since we're doing it with respect to x, we want to see what happens when x changes. So we're going to take the limit as h approaches 0 of f of a. Now, a is like the x-coordinate, and we're going to add to the x-coordinate, but we're going to keep the y-coordinate constant. So f of a plus h, comma b minus f of ab. And I hope you see the parallel to the one above, all over h. And for notation purposes, we say this is the derivative of f with respect to x at the point AB. And in this particular case, again, h refers to delta x. In a similar manner, par z, par y, the partial derivative of z with respect to y, at the point AB is the limit as h approaches 0, f of a, and then b will change incrementally, minus the initial point, f of ab, all over h. For notation here, this is the partial derivative of f with respect to y, and it's at the point ab, and in this particular case, h is delta y. I'm going to use this table of values to illustrate this partial derivative at a particular point. Z is a function of x, y, as it says in your notes, and I've given two different options here. We can say that f of x equals the temperature, let's just say degrees Fahrenheit, where x and y is inches, and I just made that up just so we can put some context to this. Or f of xy is some altitude, height of a mountain or some valley range, and x and y could be in kilometers. Okay. So the first thing we want to estimate is the partial derivative of f with respect to x at the point 1, 4. So at the point 1, 4, the temperature or altitude is 8.5. And we want to figure out what is the instantaneous rate of change in that temperature as we move in the positive x direction. Now, if we use what it actually equals, we would say the limit, I can say h or I can say delta x equals 0, then that would be f of 1 plus some delta x, comma 4, minus f of 1, 4, and f of 1, 4 is the 8.5, all over delta x. But that's what we want to approximate. Now, there are several ways to approximate. You can simply do the difference of f over the difference of x. You can use what I've circled there in green. You could also pick these 2 points, the difference in f over the difference in x, What I like to do is what we talked about last year was average rate of change on a nearest neighborhood. So I like to pick points that sandwich or go around the point in question and find the difference in f over the difference in x there. So I'll represent this approximately f at 2, 4 minus f of 0, 4 all over 2 minus 0. So the change in f over the change in x, and that's going to equal 4.5 minus 12 over 2, and that comes out to be negative 3.75. We have two different options for units. That could be degrees Fahrenheit per inch. That could also be miles per kilometer. Now I'll put in words what the interpretation is here. So the temperature decreases approximately 3.75 degrees Fahrenheit per inch as we move in the positive x direction away from the point 14. Or if we use the mountain context, the altitude decreases approximately 3.75 miles per kilometer as we move in the positive direction away from the point 14. Okay, next one. The partial derivative of f with respect to y at the point 14. Let's draw what we're trying to find here. So at this point, what is the rate of change in our function f as we increase in y? The exact answer would be the limit as delta y approaches 0, f of 1, 4 plus delta y minus f of 4, which we said was 8.5, all over delta y. And that's approximately, using average on the nearest neighborhood, is going to be f of 1, 5 minus f of 1, 3. Please note there are several ways to do it. I'm picking the points around it. That is not the only way to do it. And so what does this come out to be? 9 minus 7 over 2, which equals 1. Now the units are all the same for these problems. It's either degrees Fahrenheit per inch or miles per kilometer. And the interpretations are basically the same, differences being in which way we are moving away from the point. Okay, now we're finding the first partials, or estimating the first partials at the point 42. Okay, so this is going to be 6 minus 6 over 2, which equals 0. 0 degrees Fahrenheit per inch, and that makes a lot of sense here because as we move in this direction, the function is not changing. So that's constant along y equals 2. F partial with respect to x is 0. And then the partial derivative of f with respect to y, that's going to be the difference, 5.1 minus 5 over 2, change in f over change in y, and that's 0.1 over 2, or 0.05. That's also a very small number, close to 0, and as you see here, as we move away, this is getting smaller, but when we went from 5 to 6, it got a little bit larger, then a little bit smaller, so it's like a little bit of a bump there. Next, we're going to take a look at this contour map if this is a valley, or an isothermal map if this is a plate with temperatures on it. We're going to estimate the instantaneous rate of change in f with respect to x at the point 10, negative 1. Let's highlight that point here in pink. 10, negative 1. And we want to see what happens incrementally in the temperature or incrementally in the altitude as we move in the positive x direction. I'm going to use 2 points that I have information on, have the f value for. So I went along the x to this point, and I'll go backwards to about this point. Now this is all estimation business, so we don't have to be perfect. I just want you to get the concept here. So this is going to be approximately f at, let's call that 12.75 comma negative 1 minus f of, let's call it 8.25 comma negative 1 all over the change in x, which is 12.75 minus 8.25. All right, so what does that come out to be? Well, it comes out to be 12 minus 12 all over 4.5, and that comes out to be 0. If I use temperature for a moment, that's going to be degrees Fahrenheit per inch. Now, does that make sense to us? It does to me. See, if I'm on this point and I'm moving in this direction, you'll notice that the level curve sort of has a plateau if we move along x. So, said differently, if we move in the x direction, it's almost as if we are staying on the level curve. And you should remember from earlier in part 1 of the lesson, if you're moving along the level curve, that means the function's value is not changing. Now for the partial derivative of f with respect to y, here's our point at 10, negative 1. I'm going to pick a point on a level curve up here and a point on the level curve down there, and I'm going to use that in my estimation. So this is going to be f at 10 comma 0 minus f at 10 comma negative 1.75. That's my best guess. All over 0 minus a negative, so 0 plus 1.75. Okay, so that's going to be 8 minus 12 over 1.75, and that comes out to be negative 4 over 1.75. As a fraction, that's negative 16 over 7, or as a decimal rounded, it's going to be negative 2.29. I'll use the altitude here. Let's say miles per kilometer. So if you move in the positive y direction, the altitude is decreasing. If you move in the positive x direction, the altitude is approximately staying the same. Or if you move in the positive x direction, the temperature is staying the same. If you move in the positive y direction, the temperature is decreasing. Positive y direction. So that makes sense here because the level curve, if I follow that level curve, it had a value of 10. And then I move towards this level curve, and this level curve has a value of 8. So I do see that the temperature is decreasing. In this problem, we want to determine the sign, whether it's positive or negative, the partial derivative of f with respect to x at point P and partial derivative of f with respect to y at point P. So let's get going on that. Okay, so the instantaneous rate of change, one of the ways I like to see this, so if I'm trying to find the partial derivative with respect to x, that means the y is held constant. So if I drew a plane here, and this plane, now pardon me, it's not the greatest plane ever, but that plane is y equals b. In this case, I don't know, y equals negative 2 or something like that, but y is constant. And then if I look at the trace along that y, then I have sort of that shape there. And what I'm looking for here is if I drew a tangent, so a tangent at this point would look like this. It would be on that plane. This plane could extend, be on that plane, and there is the tangent line. I would also like to note that this is the positive x and this is the positive y. So in trying to determine if the partial derivative is positive or negative, I want to know what happens to the function as x increases. So x increases is in this direction. So you can see from this tangent line that as x increases, the tangent line is pointing downward. So it has a negative slope. So we'll say the partial derivative of f with respect to x at point P is less than 0 because that tangent line is pointing down. Now it's hard because you could say that it's pointing up and pointing down, but remember, it's what's happening as we move in the positive x direction. And to just put this to words, so as x increases along y equals b, the function goes down. The slope of the tangent is negative. So now, are you able to determine the partial derivative of f with respect to y at point P? What's happening to the function as y increases? It's a little hard to tell here, but you can see that it's actually increasing. I'll draw that plane again. So this plane, and it's not a great plane that I've drawn, but that plane is x equals a. I don't know its exact value, it's not important. And the trace along that plane looks like this. And so then at this particular point, as y increases, the function is going up. And so we will say this partial derivative with respect to y at point P is positive. And then put the words. As y increases along x equals a, the function goes up. So the slope of the tangent is positive. Now we're going to look at the derivative function, and I'll just write some notation here. The derivative function f with respect to x at any point xy. For short, we often just write that f sub x, and we could also say par the function f of xy with respect to x, or for short there, we could just say par f par x, Leibniz notation. There is one other notation that we can use, which is a d sub x of f. That also means partial derivative of f with respect to x, and that's simply notation. The definition, how to actually do it, is what we have in this dialog box. You see, instead of a, we have x. Instead of b, we have y, so that we have the function. And this function that we found right here, what does that give us? This function represents the rate of change in f as x increases if we hold y constant. Said a little differently, along any plane y equals b, the slope of the tangent is this function f sub x. Here I'm trying this drawing again. I have this plane y equals b. It's some constant plane. The trace on this curve is this parabolic shape, and then a tangent at any point. In a similar way here, we have the notation for the partial derivative of f with respect to y. And in the diagram, the plane x equals a cuts into the shape, creating that blue trace, and then we have tangents along that blue trace, and the slope of that tangent is fy. We're going to finish off this lesson showing you the very simple technique to find first partial derivatives. Okay, the first one we are going to find is the partial derivative of f with respect to x, or par f par x. So what we need to do here is simply hold y as constant. I'm going to rewrite it over here. Even though I would ordinarily not do this, I'm going to put all the y's in front because they are constants now and they serve as coefficients to the x terms. So 2y is the coefficient, or negative 2y is the coefficient of x squared, and then this thing finishes off with 3x. So let's do the derivative process. This is the same as last year. So our exponent is 3. I'm going to use the power rule. I'm going to bring that 3 down, and that 3 is going to combine with the other constant that is there, and so 3y squared serves as the coefficient of x, and I reduce the power by 1. So that's just the power rule. Minus, so I'm going to bring that 2 in the exponent down to join with the negative 2y, so we have negative 4y x, and reduce that exponent by 1, plus, and then the derivative of 3x, the coefficient of x is 3. So there we have it. Now we're going to find the partial derivative of f with respect to y, or par f par y, and we're in good shape here because the x terms do precede the y terms, and x's now are going to be held as constant. So for the first one, I'm going to bring the 2 down to join with x cubed. So I have 2x cubed, y, reduce the power or exponent by 1, minus, now the coefficient of y is the term negative 2x squared. All of this preceded the y, and so the derivative is just that coefficient. And then the derivative of 3x, well, since x is a constant, 3x is a constant, and the derivative with respect to y would be 0. Okay, the last example, example 2, we're going to find par z par x. Okay, so it looks like we're going to need the product rule here. We have this first term and then this second term. Okay, so I have first term Now I got to do the derivative of the second, which is e to the stuff, e to the xy, and then I have to do the derivative of the stuff. Now since y is a constant, it is the coefficient of x, so the derivative of xy with respect to x is just y. Now we have plus e to the xy, that's the second term, times the derivative of the first, and since y is constant, the coefficient of x is simply y squared. And the partial derivative of z with respect to y, same deal. We have first term, derivative of the second, so e to the stuff times the derivative of stuff. Since x is a constant, it is the coefficient of y, so times x, plus e to the xy, and then the derivative of xy squared with respect to y. The 2 comes down to join the x, y to the power of 1.